All right, recorded is rolling. It is Tuesday, December 6th. I got a lab lined up for you guys today. Where we're gonna do this is here. I'm just gonna do this in front of you guys right here and guide you guys along this one because this could be a really good lab, but it takes some deep thinking. So I want to give you guys a little bit of guidance here as we go along this one. All right, so I know about a third of the class was out yesterday for the FCLE. So yesterday, most of the class we actually did a Kahoot on conceptual questions about rotational dynamics. If you want to catch that, that's on Google Classroom. We did at the tail end of the class look at an FRQ, a 7-point FRQ. It was a short one. Right at the tail end. Tomorrow, do you guys know what we're doing tomorrow in this class? AP Classroom. Okay, so I saw some of you guys have already completed the AP Classroom. If you haven't yet, then just have that done by tomorrow morning. So we can do that tomorrow morning, right? Okay, AP Classroom for Unit 7. All right. So got a rotational inertia lab lined up for you guys. Rotational inertia lab. You guys have this page right here. So got a table, got a space for graph, and there's a box for conclusion. I. Hey, capital letter I. That represents rotational inertia and this section, right? And kilogram meter squared. Right? So we're going to figure out what's the rotational inertia of this T-shape. Now, this is free to rotate here. You can spin this thing. Got it right here. Just stop camera. You guys didn't think I might rotate. So it takes some effort to get it rotating, but once it is rotating, it's kind of hard to stop it too because it has this rotational inertia. And we can quantify and say, like, how much does it have? We can quantify it in kilogram meter squared. Okay? Now, on the back side of this page, you guys see a space for a five-part write-up. And so the 5 parts are the question. Actually, you guys can start tackling this question right now. Right? You say, like, what is the rotational inertia of the apparatus? Right? Could that be the question? What is the rotational inertia of the apparatus? Or some version of that. You can put that in your own words. Okay? Got a space for measuring tools. So here, as we're going along today, I'll be conducting this in front of you. I'll be filling out these numbers. Might get a spare minute here or there to start filling in these as we go along. So every time you see me pull out a measuring tool, you might want to jot it down here. Or maybe you can think ahead a little bit. Think, hey, what measuring tools would you actually need to complete this? You might have some pretty good guesses. Right? I mean, there's only like a handful of measuring tools we've ever used in this class, but like 4, 5, 6 measuring tools. Right? One of them might be a meter stick. Oh, does somebody have a stopwatch? I do need somebody to measure time today. So somebody got a stopwatch out? Right? Might jot that down. Have a volunteer here to a couple minutes. Data gathering procedure. So what variables are we gathering? And you can use this table as a checklist, right? Because I mean, what variables are on this table? Might be things we measure that are relevant to ultimately figuring this out. Data analysis. How are we going to crunch some numbers, maybe apply some equations, something with a graph, right? And it has set up a graph here. So it's going to lead into this graph. So think real close about what variables are on these axes, what equations have you guys seen recently, okay? And then conclusion, which is the answer to the question. Well, if the question is what's the rotational inertia of that apparatus, then the answer would have to be, actually, I bet the answer could be this right here, right? Some number of kilogram meters squared, right? Can that be the case? Right? Right. So, the way we're going to do this, the experiment's going to involve this. Going to put this like different weights, different lab weights here. I can know what the masses are. Say in grams, we could convert that to kilograms. Okay. Going to let this fall. Now, see how the string is like wound around this post, which has some radial size, and that's going to get this whole thing. Okay, it's going to get this whole thing spinning, right? When I say radial size, see, I'm talking about just like that's probably about a centimeter or so. Of course, we're about to measure it though anyway. I think it's providing some torque right here. That's some torque. Let me show you. Okay, you guys remember like this, right? Okay. So let's see. There's some force, right, which is this right here, crossed with this very small radial distance, which is probably about a centimeter, but we'll measure it to get a more exact number. Okay. Yeah, you guys see some torque going on? And these would be at 90 degrees to each other, right? This R and this F. Okay. Is it? Let's see here. Do you think that this lab weight as it's falling, do you think it would be accelerating like faster, faster, faster? Now it might be accelerating really slowly, but probably would be accelerating, right? Okay. Do you guys think that the tension in the string would be really close to the weight of that mass, but what, a tiny bit more or a tiny bit less? probably a tiny bit less. Right? You guys remember like an elevator accelerating down, the tension pulling it up is a little bit less than the weight of the elevator itself. Right, make it something like that. Right. All right, so there's some thoughts going to that. Okay. Now, so this whole thing's gonna like rotate, right? In fact, the more rotational inertia it has, probably the slower this would accelerate down. Right? Once you guys see the big picture before you start plunging into a bunch of numbers. Okay. What do you think would happen if I pop these arms off? Okay. What if I do this? I could pop this thing apart, right? What do you think that lab weight would do now? Do you think it's going to go down really fast, really slow? Oh, really fast, like really fast, right? Versus if I throw these arms back on, pop back in place, it gives it probably a lot more rotational inertia. It's probably slow the system down. Okay. No, we can look at that experimentally just to make sure that's actually true, but just think ahead a little bit. Right. And you know what? There's actually another perspective I can use to get an estimate of what the rotational inertia is before we touch anything physically at all. Okay. Doesn't it look pretty similar to this one right here? Okay. Like this rod rotating about its center. Okay. I thought we could use this to get a pretty close estimate of what the answer should be. Okay. So I measured ahead of time the mass of each arm. I got 143 grams each. Okay. I mean, it's pretty close to uniformly distributed. Right? The center mass is pretty close to geometric center for each one. So if I punch those numbers into the calculator, here we go, in the calculator. Okay. So let me try this version of it. I'm going to run 1/12 ml squared. So I've got 1/12 times the mass of the whole thing. Now, that's two arms of 0.143 kilograms each. Right? Because each one was 143 grams. Okay? 143 grams. Okay? Convert that to kilograms. Times the full length of the whole thing squared. Now, if I pull out this meter stick from, okay, well, it's longer than the meter stick, right? But if I go from the center to the edge, I'm looking at like 63 centimeters. Right, from here to here is like 63 centimeters. Okay, so wouldn't the full length be twice that? So the full length is 2 times 0.63 meters, putting everything in base SI units, right? And then square that. Isn't that 1/12 ml squared? Right. Do you guys think that the central post adds very much rotational inertia? Probably not very much. So maybe if I ignore that and just focus on this part, that should account for most of the rotational inertia, right? Right. Let's see what I'm gonna get. Getting 0.0378 something. Okay. If you round that up a tiny bit, because maybe kind of the central post something, maybe about 0.04 I should be looking for. So there you go. I'm going to guess based on I equals 1/12 ml squared. Okay, yeah. So pop in numbers, pop. Right. I'm going to guess this is about 0.0. Well, here. Oh, type in the number, write the number from the calculator. 378 kilogram meter squared. Okay. If you round up a little bit, maybe 168 significant digit. That's kind of what we should be looking for. Okay, that should be the answer to this lab. Right. All right, you guys ready to get going here? Okay. Again, as we're going along, right, you guys probably already have the question written. Maybe you've got some measuring tools. Right. You guys are going to write the procedure to gather the variables, and then when you guys do equations and graphs, you guys can write some stuff here. Right. And I'll pull out a grading rubric by the end of class. So first, okay, you guys see I got a few different trials set up. Okay. It says measure the radius of the thing. So I'm going to break out this ruler. Ooh, ruler. Ooh. Okay, and let's see. Well, I see the diameter is like, I'm going to call it 2.2 centimeters. Now, if the diameter is 2.2 centimeters, wouldn't the radius be 1.1 centimeters? Okay. And then in terms of base SI units for meters, should I call that 0.011? Right? 0.011. Okay. And that would be the same all the way down. Right? 0.011, 0.011. Right. That radius is going to be the same all the way down. Okay. And that'll be like the radius is going to feed into the torque, right? Because there's string wrapped around that, right? Around that central post, that radius is going to provide a torque. Okay. Okay. What is the, right, now this column says mass. I'm referring to like this mass right here, okay, which is going to provide some weight, which is going to set the whole thing in motion. Okay. So first one up, Well, I've got a 200-gram guy on there, so let's go with gotta call it 0.20 kilograms, 200 grams. Like one of your medium type lab weights. Okay. What's the following distance? So set up those meters. Ooh, meter stick. Set that up right there. Okay. And if I go from the bottom of the lab weight to the floor where it's going to land, that's looking like about 75 centimeters. So, okay, 75 centimeters. How many meters is that? Hey, 0.75, right? I could probably just use that distance all the way down, right? Okay. How much time? Right. Who brought a stopwatch today? Who brought a stopwatch? All right, so Elijah's got a stopwatch. Ugh. All right, so we're about to time this thing. Set in place here. All right. You ready to go? And let's set this thing. Okay. Ready? And start. So starting from rest, I guess this thing spinning, speeding up. All right. This thing's falling really slowly. Ooh, does look like it's accelerating. It's really subtle. Okay. Pretty sure it's accelerating, still falling. It's about halfway down. A little faster, a little faster. And stop. Okay. Elijah, how much time was that?
29.85 seconds.
29.85. All right. Ooh, look at this next column says acceleration equals 2x over t squared. Do you guys think you could take one of your classic kinematic formulas and rearrange it to get 2x over t squared to represent the linear acceleration? Do you guys think that that might be a good data analysis step? Right, like once you've got the distance and time, it starts from rest. That sounds like 3 kinematic values, right? Starts from rest. We fell so many centimeters in so much time. Can solve for the acceleration. That might be a really good analysis step to solve for the linear acceleration. Okay. Can you get what I got? 2x over t squared. You guys know how I got that? Okay. Okay. Punch into my calculator. So 2 times 0.75 divided by 29.85 squared. Okay. Now it's a tiny, tiny acceleration. 0.00168. 0.001. Well, about 0.0017. That's how much room I got to write. Okay. What is the tension in the straight? Now the tension would be the force that's provided, right? Okay. So like whatever the tension is in the string, that's the force that's providing the torque. Right? You guys think the tension is really close to the weight? Right? There should be a tiny bit less because this thing actually is accelerating down. Now it's accelerating down slowly. Might be like a shade less than the weight of the mass itself. So m times g minus a. Ooh, can you guys also derive that? Right? Do I have? Yeah, the answer is on a poster in the middle of the room, back there on the ceiling. Right? Do you guys see like an elevator accelerating down? It's right above the wrench. I guess that. And so you should be able to do this yourself because we've done this a few times in the last few months. Okay. But I bet that would be a good analysis step to be able to calculate the tension in the string, right, for a falling object. M times g minus a. Can you guys derive that from scratch? So got the mass of 0.2 kilograms. G, let's use 9.8 meters per second squared for g. Okay, minus the acceleration of 0.0017. Yeah, it's 9.8 minus 0.0017. I mean, you guys really do say it's kind of a rounding error, right? Right. So in this particular case, really, if you use the weight itself as the tension, I mean, it'd be like so close, probably not really throw it off there, right? Okay, so I'm looking at like 1.96 newtons weight. Okay. Like, what would happen if I didn't subtract off the acceleration? Okay, I mean, I still get the same number, pretty much. Yeah. So it's really just a rounding error anyway. Okay, but if it was like significant acceleration, then you would have to definitely do it that way. Okay. Angular acceleration. That's a over r, right? Isn't that that's this poster hanging right up here? Right? Like rotational kinematics, converting back and forth between linear and rotational stuff. Okay. So take this linear acceleration, which is the 0.0017 meters per second squared, divide by the radial size of 0.011 meters. I'm looking at 0.155 radians per second squared. You guys getting that too? About? Is that what you guys getting? Okay. Tell you exactly how to get it, but show this from scratch too. Okay. And finally, the torque. The torque. That's R across F. Well, here's R. The tension is the force F. So kind of just multiply those two together. They're at right angles to each other already. Right? So R cross F. I'm looking at 0.022, I'll call it. That could be Newton meters of torque. Newton meters of torque. Right? All right. You guys got that? Yeah.
The angular acceleration of that 0.015.
Did I mess that up? Let's see. Acceleration is 0.0017 meters per second squared divided by 0.011 meters radius. Okay. Are you guys getting what I got for angular acceleration? You guys get that too? Okay. All right. Yeah, because every once in a while I make a mistake, but I think that's the number. Yep. That's it. All right. Let's do you guys know that one of your points for the other, okay, you're going to get an FRQ in May. That's going to be experimental design. And one of the steps is always going to be like do multiple trials, right? Right. Are you just going to write that somewhere back here? Like on your data gathering procedure, it's going to be one of your steps, multiple trials. You guys going to write that? Okay. Yeah, let's try that here. Okay. Let's just repeat exactly what we just did. Right, so, whoops, I have to wind this thing up again. Okay. Let's do this real fast. All right, so Elijah, you got your stopwatch up?
Yep.
All right. All right, ready and go. And stop. All right. Okay. Gonna wind this up, get this ready for next time. It's right back there. All right, so Elijah, how much time was that?
34.18 seconds.
34.18. Guys, the fact that it took a little bit more time, does that mean the acceleration is going to be a little bit more, a little bit less than what we got before?
Less.
Yeah, a little bit less, right? It's going a little bit slower. Okay, so it's the same drop distance. Let's see, 2 times the falling distance divided by that times squared. Okay. Do you guys figure out how to derive that? 2x over t squared? That's 0.0013 meters per second squared. Okay. Well, you know, but it's still going to be the same tension, right? Because the acceleration is so tiny compared to free fall. Okay. angular acceleration, take that value, the linear acceleration, divide by 0.011 meters, you get 0.117. Okay, okay. And then torque, R cross T. So here's your R, 0.011, tension is 1.96. It's the same torque. 2. Okay, right, so got a little bit different angular acceleration. I mean, it's pretty close though, right? 15 compared to 12. All right. Let's save a little bit of time. We're gonna skip that down here. We're gonna change out the lab weight. Well, let's go a little bit bigger. Let's throw on 500 grams. 500 grams. Yes, if I'm throwing on 500 grams, what's going to happen to the acceleration? Yeah, it should increase, right? Here. All right, ready? Oh, nope, that was straight on. Back here. All right, so ready to go?
Yep.
Ready? And go. Oh, no, sorry, stop. We're going to start that over again. Okay, so restart. Okay, ready? And go. And stop. All right, how much time is that?
15.08 seconds.
15.08. All right, you guys write that down. I'm gonna wind this up and get a second go right here. So you guys got 15.08 seconds. 15.08. All right, next round. All right, so the same 500 grammer right here. All right, ready? And go. No, stop. All right, all right, ready? And go. Stop. All right, how much time is that?
15.55 seconds.
15.55. All right. Wind this up for next time.
Yeah.
There you go. All right, so with 0.50 kilograms, it was like the same falling distance. It was 15.08 and 15.55. Right. Right, so 2 times 0.75 divided by 15.08 squared. I'm looking at 0.0066. And then the one beneath that. 0.0062. Those are meters per second squared. Okay. The tension, I'm just gonna round the tension to the weight itself, just like before. So 0.5 kilograms times 9.8 meters per second squared. We'll just call it even 4.90 newtons. Okay. Okay. This is probably like a tiny bit less than that, like 4.89 something, but okay. Okay, angular acceleration. Let's go this linear acceleration, 0.0066 divided by 0.011 meters. So, oh wow, that's an even 0.60. That's radians per second squared. It's rotating. And then put 62 here, get 0.56. 564. How about that? Okay. Ooh, now this is interesting. You guys see how the mass and therefore the weight, it didn't quite triple. It more than doubled. It didn't quite triple. Right? And the angular acceleration looks like it went up by what? At least 4 times, but maybe more than that. You know, just like eyeballing these numbers. Okay. We pin down that relationship too. Okay. And the torque, R cross F. So let's do 0.011 cross the 4.9 newtons, getting 0.054. Just like that. Like I said. Okay. You guys making some progress on this write-up too? Okay, so you should have the question. You guys need to keep track of the measuring tools we've been using. I bet these first 4 columns, you guys are writing like how you're going to measure each one of those with those measuring tools that you mentioned before. Okay? And these last 4 columns, and then leading into ultimately the graph. Okay? You guys are going to write down here, right, step by step. Have a point for each one of those, right? Okay. All right, switch up the slab weight. Let's go with, oh, I got a 1 kilogram guy right here, 1 kilogram. There. All right, this one's probably gonna go real fast. All right, so Elijah, you ready with the stopwatch?
Yeah.
Okay, ready? And go. Stop. All right, what was that time?
9.85 seconds.
9.85 seconds. Reset this for next time. All right, 9.85 seconds. Okay. That's the same falling distance, 0.75 meters. This is for 1 kilogram. So the acceleration, 2 times the fall distance divided by the time squared. That's 0.015 5 if you want to, that'd be meters per second squared. Okay. The tension should be 9.8 newtons, pretty close to, maybe 9.79 something. Okay. And then the angular acceleration, let's go linear acceleration, which we have right here, divided by the radial size, 0.011 meters. I'm looking at 1.405. What that? That'd be radians per second squared. Ooh, look at that. Now it jumped up even more. Okay? I mean, from the last trial to this trial, we doubled the mass, therefore doubled the weight. And it looks like the angular acceleration went up by a little bit more than double, looks like. Double a little bit more. Okay. And then torque, R cross T. So let's take 0.011 meter radius, cross it with 1.405. No, scratch that. Oops. The tension, 9.8 newtons. Okay, that's 0.108. Right, do 10 meters. Yeah, 0.108. Okay. You guys get this too? Okay. I'm just following these steps right here. So the first 4 columns are measurements, the next 4 columns are calculations. Okay. Okay. I'm gonna skip the second trial for this one just to save us a little bit of time. Okay. Let's go, but you guys get in principle, you want to do like multiple trials. Okay. How about 100 grams? Ooh, have this 100 gram guy right here. Guys, 100 grams, how many kilograms is that?
0.1.
0.1. All right, 0.1. Okay, so we're about to do 0.1 kilograms. Right now. All right, ready with stopwatch? Oh, yeah. Spell out. Yeah. Step here. All right, ready? And go. Ooh, you know what? All right, I think that one petered out. All right, so you guys see how it's not actually, well, okay, it's like barely moving, right? You guys see that? Do you think there's actually a little bit of friction involved in the setup? Right, like I tried to get rid of most of the friction. Think there's a little bit? Do you think here? I think that this weight might just barely be bumping up against that frictional torque to even get this thing to move. Right. So, what was the smallest weight we used so far? Looks like double this. I'm gonna throw in another 50 grams and see if I can get this thing to go because we're kind of running like it's the lower limit. I wonder what that's gonna look like on the graph too. So we're gonna restart this. We're gonna restart. Okay, so I have 150 grams. Okay, 150 grams. I bumped it up a little bit. The 100 grams wasn't quite cutting it. All right, ready? And go. All right, yeah, it's going. Super slow. I think you guys have a hot minute to do some lab steps. All right, and stop. There you are. Okay, how much time was that?
46.98 seconds.
Ooh, 46.98 seconds. 46.98. Let's back up. Right, so with 0.150 kilograms, same fall distance we've been using. Said it was, what did you say, 46.98?
Yes.
46.98 seconds. Right, yeah, thank you. All right, so 2 times 0.75 meters divided by 46.98 seconds squared. That is, ooh, tiny, tiny, tiny number. 0.0007, about 1 digit. Okay. Take the mass, multiply, well, let's do mass times gravity, about that. We've been doing all along. 1.47 newtons of force. Okay. Take the previous linear acceleration, divide by 0.011 meters radius. That's 0.062 about meters or sorry, radians per second squared. Okay. And finally, torque 0.011 times 1.47. Okay. Looking at 0.016 meters. All right. All right, you guys good so far? Yes.
What'd you
for the acceleration, this one right here. Got point triple oh seven.
Teachers, could you please allow the early college students, 10th graders, to dismiss at 9:25 for the bus to pick them up at the front of the school? Again, 9:25 for early college students for the bus. Thank you.
Anybody want to get on a 10th grade bus? All right. All right, so we could do one more, but want to make sure that I fit everything in for the bell. So we'll just go with this data. Okay. All right. And then of course in principle you get like multiple measurements per each one. Yada. But let's graph what we have on this set of axes. We'll be able to finish this off from here. So I guess you have torque versus angular acceleration. That's tau in Newton meters. I'm just blowing this up for the video. Okay. Versus alpha in radians per second squared. Right. Now, why would I pick that as a set of axes? Remember the question we're trying to answer is what is the rotational inertia? Okay. So what do these variables, torque and alpha, have to do with rotational inertia? What's the connection? Yeah, it should be the slope, right? Right? Because you guys remember the breakout. Okay. So we've been doing this, torque is R cross F. But don't forget that this is also true. Torque is equal to I times alpha. Hey, does this look like y equals mx? Y equals mx? Now, when I say m, I'm talking about slope of a graph algebraically, right? Okay. So if I had this on my y-axis and this on my x-axis, this would be the slope, wouldn't it? Which is what we're trying to get. You see it? Okay. Hey, do you guys think maybe if I asked this sort of as a quiz question, and I had something rotating, and you could look up in that table and figure out what the moment of inertia was, right? Like for a solid cylinder, it's 1/2 mr squared. For basketball, it's 2/3 mr squared. Could you substitute that in for I and maybe solve for something else if you had to? You think you could? Okay. But that's what we're solving for here. Yeah. So I bet it's going to be the slope of this graph. Do you guys think this graph's going to be like linear? Right? Probably so. Now let's see. What were our alpha values? That's this column here, and then our torque values are this very last column. Right? So this is like y and x, right? XY, right? So what's my largest alpha? I think it's this guy right here, 1.4. So can you guys scale this up to here? Let's go like 0.5 radians per second at a time, or radians per second squared. How about that? 0.5, 1, 1.5. So 0, 0.5, 1.0, 1.5. That'll cover all the data there, right? And then for torque, the largest torque was 0.108. So let's go. Yeah, I think that's what we do. Right. Let's go 0, 0.025, 0.50, or 0.050, 0.075, and 0.01. 0, 0.025, 0.050, 0.075, and 0.10. Right, and then our large torque is just a shade above that, so it'd be pretty close to that, right? Okay. All right, you guys get that? All right, so this space will be able to handle all the data points. Okay. So we're gonna treat these like XY coordinates. And we really have 6 data points, so these should be pretty close to each other. These should be pretty close to each other. So it looks kind of like 4. It's kind of like 4 that we can sort of try and keep like averages. Okay, so when there was an angular acceleration of 0.117, that's about here. The corresponding torque was 0.022, which is about here. That's nice, pretty close. When the angular acceleration was a little bit more than that, then that was the same corresponding torque. So be like that. Those 2 points are these two guys, right? Then next one up. When the angular acceleration was 0.56 or 0.60, which is what's about here, the torque that caused that was like 0.05, a little shade over 0.05. So I'm looking at a couple of points that are probably right about there, you guys think? About there, maybe? Pretty close to. Okay. And then when the torque was, or sorry, when the angular acceleration was 1.4 something, right? The torque that caused that was 0.108, which is just a shade above the largest number I have here. So that is going to be, I think, pretty close. It's going to be right about there, pretty close to. Okay. And then when the angular acceleration was 0.06, the corresponding torque was 0.016. Wait a minute. No, I'm going the wrong way. Oops. Right. 0.05, 0.06 could be about there, right? Okay. I think it's about there. We did a little tiny one at the end. Look at that. Do all these points pretty well line up in a straight line? Like that? Look at that. And what's the slope of this line equal to? Or what physical value? Rotational inertia, I, because we got torque equals I alpha. You know what? Is there like a little bit of an intercept right here? Right? I think the intercept would actually matter in this case. I think it actually represents something. Plus something. Right? Okay. Let's think about what that could be. Guys, if you have a little bit of torque, so you have a little bit of weight. Actually, we ran into that situation. Remember, I put on 100 grams. It was like it wanted to spin, but it was like, it kind of just came to a stop. Okay. So you could have a little bit of torque, but no angular acceleration. And we were like right at that point, right, with about 100 grams. Right. So what do you think this torque represents?
Friction.
The friction you have to overcome to get it to spin in the first place. I'll call this tau FR. So the frictional torque that you have to overcome to get this whole thing spinning in the first place. Now, once you have it spinning, once you've overcome that frictional torque, everything beyond that goes into, well, angular acceleration. Okay. Is that? Yeah. Y equals mx plus b going on. Okay. All right. So let's see. Can we figure out what's the rotational inertia? Well, maybe I could just pick. How about this point and this point? Do a rise over run. Okay. How about between or let's do between the big guy and the little guy. Okay. The 1 kilogram and the 150 grams. Okay. Let's do rise over run. So this rise right here, torque. What's the difference between my largest and smallest torques? So that's 0.108 minus 0.016. You guys get it? Okay. So the change in torque here is 0.092 Newton meters. And the run is the difference in angular acceleration. 1.405 minus 0.062, right? The difference between these two angular accelerations. Okay. And the run of this is 1.343, that's radians per second squared. Okay. So if you do rise over run, right? Okay. Shouldn't that be the answer to this right here? Right? Did you guys write that maybe as your last or one of your last steps for data analysis? If you take the slope of torque versus alpha, that'll give you rotational inertia. Okay. So do that. What's 0.092 divided by 1.343? Okay. Guys, what am I hoping that this number is really close to again? Something like this. Remember before we ever touched it at all, we said theoretically it should be about this many. Okay, let's see if it is. 0.0685. Yeah, look, it's definitely the same order of magnitude. Maybe it's about 50% bigger than what we had estimated, but that's right in there, isn't it? Yeah, I can go with that. I can believe that. Right? All right, check that. So you guys have the data, you guys have a graph, you guys have the answer, and you guys have the write-up on the back. Right up on the back. Okay, because I have a scoring rubric for you guys. And this is going to be out of 12 points. I tried to make it out of 12 because I tried to force it 12 points because the real deal you guys get an A is going to be 12 points. So. Okay. All right, you guys ready for this? Okay. Yeah. You call those PVC pipes, arms. Got a central axle here. There's a pulley, there's some lab weights of the central axis. Yeah, radius of the central axis. All right. All right, well, we got 3.5 minutes, so let's do this real fast. All right, guys, go ahead and grade yourselves. All right, so question, what is the rotational inertia of the, okay, it's a type system about central vertical axis. Oh, because the axis rotates about matter stupid, right? All right, so you guys have a question, right? So about rotational inertia. Measuring tools, do you guys have maybe some, well, I guess you said if you know the lab weights, maybe you could have to just say that. Great. So you guys definitely have a ruler or a meter stick. You guys definitely have a stopwatch, right? Great. These bottoms you definitely need. It's a good idea. It also includes some kind of scale because we were measuring like masses or weights. Do you guys have data gathering procedure? I have 6 points for data gathering. Right, you guys ready for this? Right. So one is just very briefly describe the setup. Set up a pipe system to rotate about its vertical axis. Tape string to the vertical central axis of the pipe system, wind the string around the axis, route the string through a pulley so that a lab weight can be suspended and allow it to fall vertically, causing the pipe system to rotate. Right, so 1 point for just a brief description. I'll have exactly what I have. They said something about the apparatus. Okay. 1 point for measuring the lab weight, or if you said you have it somehow, if you said, just like a known value for lab weights, if you mentioned something about knowing what the mass is or measuring the mass. 1 point for using the ruler or the meter stick to measure the radius of the central vertical pipe. Okay, so 1 point for measuring the radius. 1 point for using the ruler and the stopwatch to measure the falling distance and the corresponding time. You might have that in 2 separate steps. I was trying to condense this a little bit. Okay. Right. So what's the falling distance? What's the time? That's really 2 different things, right? Okay. Don't worry about those 10 revolutions. So that doesn't really matter. We just did it till it fell on the floor. Okay. Oh, do you guys have multiple trials? Okay. Repeat for 3 trials per lab weight. Right. I know we only did 2 for some of those, but we have a little time here. 1 point for repeating process with 5 different masses. Did you guys clearly identify an independent variable? That's another thing that AP definitely cares about, but I mean, that's really good practice in science in general, right? To have an independent variable. Right, you guys got that? Independent variable? Right. We're changing out the masses. Data analysis. So here's the other 6 points. Okay. Did you guys get average acceleration? This was one of the first formulas, guys. You guys remember Paul Hewitt going to mine shaft? Right. It's about 125 meters deep. Wasn't that x equals 1/2 at squared? Right. If you rearrange that, that's how you get acceleration. You guys remember how to do that, right? That's where a equals 2x divided by t squared comes from, right? Okay. 1 point for determining the tension. So tension in an elevator table, net force equals mass times acceleration. That's student cycle of motion. The net force is the weight down minus the tension up, which almost a wash, but not exactly, right? Okay. So then if you rearrange that a little bit, you get tension is equal to m times g minus a. Now, a was so small compared to g, it was basically just mg. We kind of rounded to that anyway, but in general, that'd be a good thing to know, right? Okay. You guys could derive this because there's a good chance you're going to have to do that in May. 1 point for determining angular acceleration, which is linear acceleration divided by the radial size. 1 point for determining torque, r cross f. 1 point for graphing tau versus alpha. And 1 point for determining the slope and then getting the rotational inertia. So there you go. All right, so throw that in the great shape for you guys to take off. All right, that is our wrap on today.